Hello everyone, welcome to the first part of the presentation about areas of surfaces obtained by rotation of graphs of functions. This presentation is divided into three parts, and namely in the first part we will use elementary methods to derive the formulas for the surface areas of a cylinder, cone, and a section of a cone called frustum. In contrast, in the second part we will use non-elementary methods to derive the general formula for this area of the surface obtained by rotation of the graph of a given function. And finally, in the third part, we will use the integral formula obtained in section 2 and we will apply it to a sphere. And we will prove a remarkable theorem by Archimedes about a sphere and its circumscribed cylinder. So let's go to the first section and let's handle the case of a cylinder. So let's assume that we have a cylinder with radius r and height h. And I marked here the given parameters of the cylinder in blue color. So let's assume that this cylinder is painted with ideal paint and which transfers completely and perfectly onto whatever surface it is rolled on. So let's roll this cylinder, say, on a wall, and you will see that after precisely one revolution we will obtain a rectangle whose area is exactly the same as the area of the original cylinder. So the question is, what are the dimensions of this rectangle? Well, its width, the rectangle's width, will be equal to this, to the height of the cylinder, of course, and the rectangle's length will be equal to the circumference of the cylinder. Now, the circumference of the cylinder is equal to 2 pi r because it is a circle of radius r. Okay, so in that case, in order to obtain the surface area of a cylinder, all we need to do is to multiply the rectangle's width times length, which is h times 2 pi r, and then we'll get the formula for the surface area of the cylinder, which is 2 pi hr, as we have it here. Okay, so let's handle now a slightly more complicated case, namely the case of a cone. So let's consider a cone which we assume to be made of ideal non-stretchable paper, and let's denote the radius of the base of this cone by little r and the slant height of the cone as little l. Again, I have marked in blue the given parameters of the cone, r and little l. Okay, let's observe right off the bat that the circumference of the cone is equal to 2 pi r. And that's because it is a circle of radius r. So how are we going to get the surface area of this cone? Well, we'll use a little trick. Namely, we will cut the cone along its slant height, and then we'll squash it until it becomes completely flat. So that's what we're going to do. And observe that as a result of the squashing, we're going to obtain a circular sector whose area is equal to the area of our cone. Now, the arc of this circular sector will be of the same length, 2 pi r, because during the unfolding of the cone, paper did not stretch. Now, however, the radius of the cone will be little l, and it will not be the radius of the original cone's base r. That cone's base radius is no longer visible on this picture. Okay, so we have reduced the problem of finding the area of a cone to the problem of finding the area of a circular sector with the given radius and the given circumference. Let's call that circumference little c, and we see that this little c equals 2 pi r. Okay, so how do we go about finding the area of a circular sector, which here on this picture quite surprisingly reminds us of the hit computer game of 1990s, Pac-Man. But seriously, what we're going to do, we're going to experiment. So first, let's consider a circular sector in the shape of a 90-degree pizza pie. Observe that the length of the red arc is equal to the quarter of the length of the whole circumference, because the whole circumference consists of 4 arcs like that. Similarly, the light blue area of the sector is quarter of the area of the whole circle, because the whole circle contains exactly 4 parts like that. Hence, the proportion of the circumference that is covered by the red arc is the same as the proportion of the area that is covered by the light blue sector. So we can, in general, we can write this equality of proportions here, namely that the red circumference to the entire circumference is equal to the blue area divided by the entire area. If we now denote the light blue area that we are looking for by capital A, we can write the equality of the two ratios in the following form, namely little c divided by 2 pi l is equal to capital A divided by pi l squared. And pi l squared and 2 pi l because the radius of our circle in question here is little l. So let's take this last equation here and let's multiply it by pi l. We're going to receive c over 2 divided by a over l. Now standard cross multiplication will give us the area of the circular sector, and that will be the circumference times the radius divided by 2. But we remember that circumference in our case was equal to 2 pi r, so as a result we obtain the final formula for the surface area of a cone, and that's pi times slant height times radius of the base. Okay, the last surface that we will handle with the help of these elementary methods will be the surface area of a frustum. So what is a frustum? So frustum is obtained from the cone by cutting the cone along a plane which is parallel to the cone's base. So we basically chop off the top part, which is colored here in magenta, and what remains is the frustum. And the area we are interested is marked here in the black color. So a frustum is determined by 3 parameters, namely the radii of its upper and lower bases, so namely r sub 1, r sub 2, and by its slant height little l. I marked, as before, the given parameters of the frustum in blue color. Okay, so how do we go about finding the area of the frustum? So first, we will introduce an auxiliary parameter capital L, and with help of this parameter, it will be much easier to derive the final formula. So let capital L be the slant height of the original cone, the large cone our frustum came from. Okay, so it turns out that we can readily calculate capital L. So in order to do that, let's look at the at 2 triangles, 2 right-angled triangles. The first triangle is the little triangle, determined by the vertex V of the cone and the smaller of the bases, and that's with length r sub 1. And the second triangle is the large triangle, which consists determined by the vertex of the cone and the larger of the bases, r sub 2. So let's observe that these two triangles have their corresponding sides parallel, and therefore they are similar. We can therefore claim that the ratios of corresponding sides are the same. So let's take the ratios of r sub 1 divided by r sub 2, and we know that that ratio has to be equal to the ratio of the small hypotenuse divided by the large hypotenuse. Now, the large hypotenuse is capital L. Now, the small hypotenuse is capital L minus little l. So I have written the equality of these ratios here in the black equation, and we will apply a sequence of transformations to this black equation, obtaining each time equations of a different color. So let's look at the black equation, and let's focus on its right side where we have a fraction, and let's divide the numerator and the denominator of that fraction by capital L. Now, in the denominator we have capital L, so when we divide it by capital L we get 1, and effectively the denominator disappears. So we are left basically with the numerator, and we obtain this red equation where we have nicely isolated the ratio of slant heights. Let's take that ratio and let's move it to the left side of the equation, while at the same time taking the ratio of the radii to the right side of the equation. We will obtain the purple equation, and in the purple equation let's find the common denominator on the right side. That common denominator will be r sub 2, and we will get the blue equation. Now, the blue equation is very nice for extracting capital L from it. Namely, we have to use simply standard cross multiplication, L times r sub 2 divided by r sub 2 minus r sub 1. So we have obtained the formula for the auxiliary parameter L, and that's the slant height of the original large cone. Having L, finding of the lateral surface area of the cone will be quick. Okay, so what is this area we're looking for equal? How do we go about finding it now? Well, it is the difference of the areas of the large cone and the small cone, the magenta cone, which we have chopped off. So we take the large cone, we subtract from it the area of a small cone, and we know the formula for the area of a cone, so let's apply it. So in the case of the large cone, we have pi times slant height, which is capital L, times r sub 2, and in the case of a small cone, we have pi times capital L minus little l times r sub 1. So let's expand this product here. We will obtain an expression consisting of 3 terms, and first 2 terms in that expression will have pi l in common. So let's take pi l out, and we will obtain now an expression where capital L is just in a single place. We have just calculated the capital L, so let's substitute for capital L the fraction we have found. So in this last expression that we have here, we see that the terms r sub 2 minus r sub 1 cancels very nicely with this r sub 2 minus r sub 1, and we are receiving namely the formula for the surface area of the frustum, pi little l times r sub 2 plus pi little l plus r sub 1. So the final formula is therefore that the area of a frustum is equal to pi times its slant height times the sum of its radii.